this video is on the topic of 5.5 indefinite integrals and the substitution rule. We are going to learn two very simple tricks today in this subtopic to perform definite integrations on function that has some specific form. So basically, we are going to learn the power rule in integral form, and also we are going to learn what we call the substitution rule. So these are the two topics or tricks that you will see in the next half an hour or so. The first thing is this. Differentiation is usually easy, right? So we learn and explain what is derivative, which is differentiation in the beginning, in the beginning parts of this course. After that, we venture into integration, and you find that integrations is usually more complicated than the differentiation. That's why you have this meme showing that you thought that you are very smart in learning all the differentiation, but when it comes to integration, things become complicated. What we're going to see is that if you see integral like this, so this is an functions of square root of 1 plus y squared times 2y times dy, and you're asked to find its indefinite integral, that is to find its antiderivative. From this topic onwards, I think we will be seeing a lot of techniques to perform integration, be the integration in the form of definite or indefinite integral. So anyway, the first thing we are going to learn today as the tricks to perform integrations is what we call the power rule. The power rule says that if you have a function that is in the form of u and you're asked to integrate it, then you use this formula. Of course, this is just a formula and people use it easily. What I want to do here is to explain how this formula comes about. Now here, u is some specific function. For example, u, just an example, say u is equals to x squared. So if you see an integration in the form of, say, x squared times 2x dx, okay? So by doing that, then this integration of x squared times 2x dx is actually in the form of u power n du. Here, u takes on the form of x squared, whereas du is equals to du dx times dx, which is equals to 2x dx, right? So 2x dx here is actually du. So we'll be looking at this example in the following lectures, in the following slides. So first of all, I would like to derive the power rule. So these are the definition. These are the derivations of the power rules in the integral form. So finally, we'll arrive at these very simple relationships that u power n integrated with respect to u is given by this. So once you have this formula, then you can apply it to calculate integrations like this form or integrations like this form, okay? So how do you obtain these power rules? The derivations of this formula can be followed in these two slides. Now, most of you would not be interested in following, most of you would not be interested in deriving the formula, but as a correct way of learning mathematics, you should try to understand the logics and the steps that leads to the formula. Instead of just memorizing the formula, you should try to understand how this derivation comes about. It gives you a more insightful idea of how the rules of integrations is applied. First of all, I would define a function which is the antiderivative of a small f. So I start off with a small f function here, and I claim that this capital function f here is the antiderivative to the small function f. Therefore, the relationship between the capital function f and small function f is a relationship between antiderivative and the function itself. The antiderivative of the small function f is such that d dx of the capital function f gives you this f. Okay, so this formula tells you that the capital function f and the function f is related to this very simple formula, because the capital function f is the antiderivative to the small function f. The other way of expressing these statements is that since fx, capital F, is the antiderivative of the small function f, you can express the relationship in the forms of indefinite integral. Indefinite integral is a symbol that is used to represent antiderivative. Right? So if you put in the small function f into the indefinite integral symbol, then this indefinite integral refers to the collections of all the antiderivative. Okay, so these are the two equivalent statements that relates the function f and its antiderivative. So now I'm going to generalize this to the case where f, capital function f, is a function of u instead, so that the u is not a simple function of x, but a general function of f. Of x. So the difference between this and this is that the function, capital function f, has only dependent on x, whereas in this case, the capital function f is an composite function. It's a composite function of u. So in that case, I would say df du is equals to f of u, where u is a function of x, right? So in the special case where u is simply equals to x, then this relationship reduced to this. Okay, so this is just the relationships that is generalized from x to u. Now, once I have written down that, then I'm going to proceed further. So I'm going to write down the derivative of the function f in terms of u. See, this is to take the derivative of the function, capital function f, with argument u with respect to x. So since capital function f of u is a composite function, I have to apply the chain rule. So I'm going to apply the chain rule. When I apply the chain rule, this is what I have, times du dx. This formula is written down by applying the chain rule to the capital function f of u. This expression, this term is the derivative of f of u, and since f of u is the antiderivative of the small function of u, then this is nothing but just equals to f of u du dx. I have this relationship that d dx of f of u is equals to the right hand side, which is the product of f of u times du dx. If you have this simple relationship, d dx of, say, a capital function g of x equals to g of x. This is just an example, okay, where capital function g is the antiderivative to the small function g. Then what you can say is that the capital function g is the antiderivative to the small function g. Therefore, these relationships can equally be written in the form of definite integral, which is to say you have an definite integral symbol, then you place the small function g in the definite integration that would represent the antiderivative of the small function g and the antiderivative of the small function g is just the function of gx. On the left hand side, you have f of u, and the right hand side here, you have f of u du dx. If you compare this to the right hand side, you compare this one to the g of f, then what can you say about this? Let us try to write this relationship into the form of definite integral. So this statement is amount to say that the f of u is the antiderivative of this function on the right. Then what is this function on the right? It's a function of f of u times du dx. And remember, if you have d dx g of something times g of something on the right, then the indefinite integral would be written in the forms of an variable x. So here we are differentiating with respect to x. Therefore, I should have an symbol of dx here. So this dx comes from here. Okay. Likewise, if you have a dx here, then you have a dx here as well. So I'm rewriting this relationship in the forms of indefinite integral. This is the antiderivative. Then this is the variable, which is dx. Then this is the function that plays a role of gx here. And here it is f of u du dx. Okay, so I have now convinced, I hope that I have convinced that I arrived at this relationship from the fact that df of u, df of u, so du df, du of f of u equals to f of u is now being translated into this form. So I'm going to further do this. So this is f of u, and then I have a product of du, dx, and dx. And what is this? This is actually the definition of the differential. So you have to recall the definition of differential that we have discussed in length in the previous lecture. So if you have product of a function u with respect to x, this is the derivative of the function u with respect to x multiplied with dx, then what you get is an differential in u. Therefore, I have here du. So what I have done is that I have successfully written this f of u as integration of f of u du, where it is understood that capital function f is the antiderivative to the small function f of u. So now I'm going to proceed further. Let me choose a form of the capital function f of u. So since the capital function f and small function f is not fixed and it's remain general up to this point, I'm free to express the function of capital F into any form I like in terms of u. So let me say the capital function f of u is a function of u raised to some power of n plus 1 over n plus 1, so that the small function f is the derivative of the capital function f. So if you take the derivative with respect to u for this, then you'll be able to derive the small function f. So if I have capital function f in this form, then my small function f will be just simply equals to u of n, right? So this statement is written down by making the assumption that capital function f takes on this particular form, and since small function f is the derivative of the capital function f, then the form of the small function f is fixed. So choosing the capital function f and small function f to be taking these two forms respectively, then I come back to this very simple relationship that I just derived. F of u is the integrations of f of u du, where here f of u is the capital function f, here is a small function f. Now I forgot to write down another thing, that is the constant. The indefinite integrals is the collections of all the antiderivative. Therefore, I should have a constant c all along. Okay, so that is the correct statements that relates the antiderivative and the indefinite integral. So I have a C. So I miss a C, so I fill up the C here. So now I'm going to slot in the expressions of f of u and f of u respectively into this relationship. Then what I would have is here I have u n plus 1 over n plus 1, and that is a constant equals to the integration of f of u. And what is f of u? F of u is just u power n, and then you have du. So that is how I arrive at the formula of the power rule in integral form. Okay, so these are the steps that leads to the form of the definite integral. Sorry, these are the steps that leads to the power rule in integral form. And then let us try to apply this to a simple example. So here the simple example we are going to talk about is this integration, square root of 1 over y. Sorry, I have to look at the correct. So this the example we are looking at is square root of 1 plus y squared 2y dy. Square root of y squared y dy. So how do you perform the definite integral to this function? Is by recognizing that you can actually cast the integrand into the form of f of u du. Okay, so as long as you can cast or rewrite or express the integrations into the form of f of u times du, then you can use the power rules integral to calculate this. So how do you do that? Then you can just try to see if you can recognize that this is actually can be expressed in the form of f of u and du. Where you identify this as du, you identify this as f of u. So I will try to make you aware that the expression of square root of 1 plus y squared is f of u, and the product of 2y dy is actually du by defining u as 1 plus y squared, right? So you define a functions of u in terms of y, where y is the independent variable. So with this, then you can calculate the differential of u. So the differential of u is by definition du dy times the dy. So you have to know the definition of differential before you can write down this formula. So if you have forgotten what is differential, you have to go back to the previous lecture to revise what is the definition of differential. We have actually mentioned that very often in our previous lecture. So that would then give you du dy is just dy, 2y dy. So then by looking at this very simple relationship, you recognize that this is just your f du. Then if you call u as 1 plus y squared, then this is nothing but just use in a square root. Therefore, here your f of u is just equals to u of half, right? So now I have been able to successfully translate the integrations. I have successfully translated these integrations into the form of f of u times du, where the f of u is just u raised to the power of half, and then I have du. Then you can apply the power rule. The power rule say if you have u of n plus 1 over n plus 1 du, then this is equal to u power n. Or equivalently, this is also can be expressed as u power n un is equals to u of n minus 1 over, let me see, what should it be? Should be n minus 1 over n minus 1, if I'm not wrong. Yeah, I think I should be correct. Okay, so that would then equals to u power minus half over minus half. So that turns out to be minus 2u half. Is this the correct answer? Technically, no, because the indefinite integral represents the collections of all possible antiderivative. Therefore, you must always include an arbitrary constant. If you do not an arbitrary constant here, then technically it is not correct. So the answer to this question would be equals to minus 2 with u raised to the power of minus half, where in this case here, my u is equals to 1 plus u squared. Therefore, this would be then equals to the square root of 1 plus y squared plus n constant. So this is the answer. Let me check if my answer is correct. So this is the expression that I have found. U power n is u power n. Let me see if my derivation is correct. U power n, maybe my solution is not correct. So I think I have derived the formula incorrectly. So yeah, I think I'm in trouble. So this is u power n. Yeah, no, I'm not in trouble. I think I'm correct. So I have arrived at this formula. It's just that when I apply the formula, I think this is written wrongly. Here I have written and used the wrong formula. The correct formula to use for this integration should be like this. Integration of u half du. So to calculate the integration of this, I should use the formula that the integration of u power n du is u power n plus 1 over n plus 1 plus c. So in this case, obviously, the n is equals to half. Therefore, the integration here would be u raised to the power of half plus 1 over half plus 1 plus c, and then it should be equal to u power 3 over 2 over 3 over 2 plus n constant, where the u is 1 plus y squared. Therefore, this will give me 2 over 3, 1 plus y squared, 3 over 2 plus c. So that is the solutions to the integrations of the square root of 1 plus y squared 2y dy. So you can always check to see whether the integrations obtained here is correct or not by using Mathematica. So let me try to do this. I'm not very convinced that my answer is absolutely correct. So I'm very curious. Therefore, I will call out the Mathematica Wolfram Alpha, Wolfram Alpha to help me check the integrations. So my integration is integrate a function which is square root of 1 plus y squared multiplied with 2y and then 2y, and then I'm going to integrated with respect to y. So this is the integrations of square root of 1 plus y squared times 2y. So this is the integration I want to integrate, square root of 1 plus y squared 2y, and is to be integrated with respect to x, with respect to y. So this is what I write. This comma y means I'm asking Mathematica to integrate this function with respect to y, and see what do I get. So interpret this correctly as this integration as 2 over 3 y squared plus 1 raised to the power of 2/3, which is just equals to the expression I got here. So I'm sure that this integration is correct. So that finished the demonstrations of the example number 1 using the power rules. So the conclusion of this exercise is that if you can cast an integrations into the form of un power n like this, any integration, if you can cast it into the form of un dn, then you can apply this formula to perform the integration. And this is just an example of integration that could be calculated by casting it into the form of u power n. U power n. How about this example? So this is another example. So let us try to cast this integration into the form of u power n du. And you have to know how to do this. So the example here is integrations of square root of 4t plus 1, and you integrate it with respect to t. So this is the integrations that we try to solve, 4t minus 1 dt. So we are going to cast this into the form of u power n dn. So you have to find out the right substitution. So it would be simply performed by assuming that your u is 4t plus 1. So what you do is just you let u as 4t plus 1. Then with that, you can then calculate the differential of u. The differential of u is du dt times dt. And what do you get? You get 4 times dt. Okay, so here you have 4 dt. Therefore, I want to make this to become 4 dt. I multiply this by a factor of 4 and divide it by a factor of 4. And then this can then be cast into the form of u, right? So since I define u to be 4t plus 1, then the square root of 40 will then be just u of half. And then this is nothing but just my du. So I have this du. So I have integrations of factor of 1 over 4, and the antiderivative of u raised to the power of half. Then this indefinite integral will just give me u 3 over 2, and then 3 over 2 plus a constant. So that is the answer, which is just u 3 over 2 over 6, okay, plus n constant c prime. But this c and c are different by a factor of 1/4. So that is another example of turning the integrations into the form of u power n and du. Okay, so that is actually quite simple. So next time when you see any integration, the first thing you would always try is to find a substitution rule of u and see if you can transform the integration into the form of u power n du. Okay, then the next formula we are going to learn is the substitution rule, which is very similar basically to the tricks that we just explained. So the idea here is this: if you see any integrations that is in the form like this. So you imagine that you have a functions of a functions gt. So if you have a integration which appears as the product of the function of g of t multiply with dg dt times dt, then this integration could be performed by turning this integration into the form of f of u du, where u is just your g. Okay. So example would be like this. Say if you have an example of, for example, let me think of a good example here. If you have a function of say sine of say x power 2 dx, sorry 2x dx, let me see, sine of power 2, sine of x squared, then 2x dx. Okay, so this kind of integration can then be expressed as the integrations of the function of g of f times g prime, so this is not g of t but g of x, and then g of x times the g dt, sorry, dg dx. Let me see, dg dx, sorry, it should be in the form of dg dx times dx. Okay, so here I'm using t as the variable, but it is the same as using x as a variable. So I'm claiming that this is an integration that is in the form of f of g of x times g of x and dx. So here, this 2x is the dg dx. So what I am assuming here is that the f of the function u is sine of u, and u is the g function, which is the x squared. Okay, so that dg dx is the same as 2x. So here, this 2x is just my dg dx, and this is the dx, and this is nothing but just a function of g of x. Okay, so anyway, this is just an example. If you have an integration that could be cast into the form of functions of a function times the derivative times the dx, then this function could then be turned into the form of f of u du. Then you can perform the integrations using this formula. So it's easier to look at an example. I'll stop at 9 because I think this is online course. Okay. So basically, this is a very simple example. In this case, we have cos of 7x plus 5, and we are going to perform integrations of this. The integrations of cos of 7x plus 5 dx. And I'm going to cast this into the form of f of u du, where u is a function of 7x plus 5. And my f of u is cos of u, and u is 7x plus 5. And then I also have to calculate du as 7 dx. Okay, so this is the differential of du. So by doing this substitution, that u represents 7x plus 5, and f, small function f, represents the cos function, then these integrations could then be easily cast in the form of cos of u, and dx is just du over 7. So by doing that simple substitutions, I am now able to cast this integration into the form, these integrations into the form of fu du, where fu is cos of u, du is just the du, and this could then be integrated quite easily. It will be just sine of u plus a constant c. So that is minus 1 over 7 sine of 7x plus 5 plus the constant. So that is the applications of the substitution rule. Then you also have this example 4, example 5, example 6, and the other example that is trying to illustrate the applications of the substitution rule. And you always remember that in performing the indefinite integral, you have to add a c, or else your c will be left behind. Then formally your answer is actually not correct.